Okay, this next section here is volume by cross sections. So we're either taking three-dimensional objects formed by cross sections perpendicular with respect to the x-axis, so that would be integrating with respect to x, or so these volumes of revolution formed by cross sections that are perpendicular to the x and to the y-axis. So in the case of us, if these cross sections were squares, I mean, we know this from geometry, just to remind us, we know that the area is going to equal to the side squared over here. So we could think of that as equal to 1/2 the side times the side, and that'd be 1/2 side squared. All right. If we have these are sides that come up very often. We could also have half a square. We could also see that's a triangle is going to equal half a square. We have that one too, where we'll have Lu, and Lu radical 2. That happens as well. We also have equilateral triangles, where if we have an equilateral triangle, we could have y down here. So we're going to have y here and y here, splitting that up. So each side is y. So remember here, that's be a right angle, so that's going to be 60. This would be a 30, 60, 90 triangle. So it's going to be y, y, and then y radical 2. We have that here. So we have that case. So we have this. We have the 60, 45, 45, 90. Sorry, 45, 45, 90. And we have the 30, 60, 90 over here. We want to remember from geometry because it's going to come in handy right here. So keep that in mind. We have the isosceles right triangle. Sorry, did that one before. I'll write that again here for you. So this is going to be S radical 2. Okay, and then the semicircle, we know if we have radius here and a radius here, our area is going to equal to pi r squared. In this case, divided by 2 because it's a semicircle. So if we have these squares, cross sections, perpendicular with respect to the x-axis, then we'd have, this one says we're going to write down the area of a square in terms of the given functions. Well, we have f of x on the top here, on the top left, and g of x on the bottom. So we're going to be subtracting f of x minus g of x. Well, that's the same on both sides because it's a square. So therefore, our area is going to equal to f of x minus g of x quantity squared. And then working our way down here. So if we have an infinite number of these cross sections, being infinite number of these square cross sections being added together, we compute that, and we get our volume. So we integrate from a to b, okay? And so that's going to be f of x minus g of x quantity squared dx. Again, so we're perpendicular with respect to the x-axis. Now, over here, we have some semicircles, okay? Semicircle cross sections. You want to find the radius in terms of the functions. So we have f of x minus g of x. Okay. Now, we have our radius, so that's going to equal 1/2, right? It's the 1/2 of this because we don't want the whole entire thing. It's 1/2 of this. 1/2 the difference of the two functions, f of x minus g of x. 1/2, and this is the radius because it's all the way across, takes 1/2 would be the radius. And then we have the area is equal to pi, it's going to be pi r squared, so it's pi over the 2 from pi r squared. And this is going to be 1/2 f of x minus g of x quantity squared. So again, it's pi r squared. Now this pi is over here, this 1/2 because it's half a circle, and then it's also half this distance, okay, for the radius. So if we square that 2 and then we multiply that by 2, our area is going to be pi over 8. We want to clean up sorry, we want to clean that up all out. See, if you have this 2 squared, it's 4, and you have the 4 times the 2, it's going to make a denominator of 8, and the pi was already out here, so it's going to be pi over 8 times f of x minus g of x, f of x minus g of x quantity squared. So if we were to, if we're going to write the solid generated by all these slices, okay, of many semicircles added together, that volume would be equal to pi over 8, integrate from a to b, again with respect to x, so it's the same thing here, still perpendicular with respect to the x-axis. Okay, so that's going to be f of x minus g of x dx pi over 8. That's the key ratio to take out there, scalar to take out there. If we had right triangle cross sections here, isosceles right triangle cross sections, like as depicted right here, all right, that are perpendicular to the x-axis, then our area of just one of those isosceles right triangles would be 1/2 f of x minus g of x quantity squared k dx. Oh, just, yeah, well, you don't need the dx because we're not integrating. Now we're going to integrate, and so we would just take the volume is equal to the integral from a to b, of the triangle a to b, okay, of 1/2 f of x minus g of x dx, and so that's going to be the volume is equal to 1/2 integral from a to b of f of x minus g of x squared dx. Alright, let's take a look on the right hand side here. On the right hand side we're talking about equilateral triangle slices that are perpendicular to the x-axis. So these are equilateral triangles, so we have to remember some of our geometry. Remember the ratio of the sides of a 30, 60, 90 triangle. You're going to see with our equilateral triangles, you're going to see a 30, 60, 90. So we have to remember that those 30, 60, 90 is going to be in the ratio of 1, radical 3, and 2. So if we divide up that right triangle, you're going to have a 30 here, you're going to have a 60 here. Right triangle right here is created. So our height is, if this is a 30, this is 60, 60 is going to be radical 3 over 2 times whatever this is. This is f, so this is f of x minus g of x over 2. So this is going to be radical 3 times f of x, minus g of x over 2. And you bring that 2 out, and so it's going to be radical 3 over 2. So this is the height. This is radical 3 over 2 times the difference of f of x minus g of x. And again, f of x minus g of x. f of x minus g of x. Okay, so now we're continuing down here. So it's base times height divided by 2. So our area is going to equal to 1/2 the base, f of x minus g of x, 1/2 the base, times the height, which we just got over here. Okay, so it's going to be radical 3 over 2 times f of x minus g of x. So this obviously equals to 1/2 the base times the height, just to bring it back, make it clear. And so that if we clean up all your constants right there, you're going to get radical 3 over 4. Radical 3 over 4 times f of x minus g of x squared. And so we're gonna use calculus to write the volume of the solid generated. So if I have many of these these equilateral triangles added together to make the volume, we would have the following. So that our volume is going to equal to the integral from a to b of radical 3 over 4 times f of x minus g of x quantity squared dx. And so that's what we'll have right there. So now we have, we're looking for the volume of the solid bounded by y equals the square root of x right here, and x equals 4. So right in here, we're taking squares this way, perpendicular with respect to the x-axis. So what we need to do there is draw the little picture to help us visualize this. This is radical x right here. Okay, and so the area of those square slices, this area is equal to side squared. So our volume is, if we integrate that from 0 to 4 of the square root of x squared dx. So that's going to equal, volume is equal to the square root of 0 to 4 of x dx. And then, so the volume is equal to 1/2 x squared from 0 to 4. And so our volume is equal to 1/2 16 minus 0. So our volume is equal to 8. Okay, the next problem is the volume of a solid bounded by a circle. X squared plus y squared is equal to 9. So we know we have a radius of 3. So we drew the circle right here. So it's y and y. And the cross sections are perpendicular with respect to the x-axis, are isosceles right triangles. So if they're isosceles right triangles, I draw a little picture here of this little wedge. So you have y and y, so this is down here, so this is a right triangle. Draw down the perpendicular, so you can have y, y, and then y radical 2. So this one also would be y radical 2. So if we have the area of an isosceles right triangle, it's going to area equals 1/2 base times height. So area is going to equal to 1/2 2y times y. So area is going to equal to y squared. So therefore, what is y squared? Y squared, if we substitute for this formula right here, is going to equal to y squared is equal to 9 minus x squared. So that's what we use to integrate. We have 9 minus x squared. In terms of x, we have it. So our volume is going to equal to integral from 0 to 3, integrating from 0 to 3 of 9 minus x squared dx. But because of symmetry, you can see that we have two parts to it, right? So that's why we have to put a 2 here in front. We're using symmetry, so that's using symmetry. Okay. And so our volume is going to equal to 2 times, and it's going to be what? 9x minus 1/3 x cubed over 3 x cubed, so 0 to 3. And so our volume is going to equal to 2 times, put it in 9, you're going to get 27 minus 9 minus 0 minus 0. So you're going to get volume is equal to 2 times 18, so it's going to be 36. Okay, again, we're going to integrate, we're going to find the area and then use that area, integrate it in order to find the volume. That's been our pattern so far. So now we're doing the bounded between these two curves, and perpendicular to the x-axis is a semicircle. So we're talking about semicircles right now. So we drew out the little curves, x equals y squared, x equals 9. And so we're going to have the area is equal to pi radius squared, or half, it's actually half pi r squared. So the area is going to equal to pi over 2 times radius squared, So our area is equal to pi over 2 times radical x squared. So area is equal to pi over 2x. So that's what we integrate. So we go over here and we integrate. And we have the volume is equal to 0 to 9. We're integrating from pi over 2 x dx. And so we can bring that constant out. So we have the volume, so it's going to equal to pi over 2 times the integral of x dx from 0 to 9. So that's going to equal to pi over 2 times 1/2 x squared, evaluated from 0 to 9. So it's going to be pi over 4 times 81 minus 0. So our volume is equal to 81 pi over 4.